Okay, so we're going to take a look at some of the data reduction and analysis from the shock tube. We're starting over here with a look at what our atmospheric pressure conditions are today in the lab. So I called out to the airport and we got the altimeter setting for this atmosphere. This is 30.09 inches of mercury. This is the setting at which, if you were sitting at sea level in this atmosphere, if you could dig a hole down to sea level, that's what your altimeter would be reading, or that's what your barometer would be reading. Excuse me a second. All right, so we're going to adjust that because we're not at sea level. We're at 5,000 feet, so we're going to subtract off 5 inches of mercury. That is 1 inch per every 1,000 feet above sea level, and that takes us to a local atmospheric pressure of 25.09 inches of mercury. We can convert that into PSI, knowing that at 14.7 PSI, 1 atmosphere, the atmosphere has 29.92 inches of mercury capability. And so we end up with a pressure here in Prescott in the lab at 12.33 PSI. This is really important to know because this pressure, the atmospheric pressure in the lab, is what is used in the equation to calculate Mach number in the normal shock relationship. That P3 over P1 in your equation sheet, P1 and P3 must be expressed in terms of absolute pressure. So P1 is 12.33 PSI, and that's the pressure that the pressure transducers are reading before the shock wave hits. When the shock wave hits at time t equals 0, we see this pulse in pressure transducers 1's trace, and it jumps. Now the jump, the amount of the jump, is proportional to the pressure that's applied as the shock wave goes by. The jump in that magnitude, if you look at the trace, you'll see that it's about 91.6 millivolts. Now there's a lot of noise on the data coming in. It's not a straight line, there's actually some noise superimposed. And then there's noise superimposed on the way out. What we want to do is look at the average of the input and the average of the output. Sometimes that's hard to do when you're looking at the Excel data. But the difference between those two levels is 91.6 millivolts. Now how do we get from there to this delta P, this pressure? Well, the key is in knowing what the sensitivity of the pressure transducer is. And if we know that, then we convert this delta V into a delta P, which we do right over here. We take this delta V in volts and we multiply it by the sensitivity, 5 millivolts per PSI, and we convert that into a delta P of 18.32 PSI, which is the delta P from ambient pressure to the pressure downstream of the shock after the shock wave passes. So we can take that delta P and add it to the incoming pressure, P1 before the shock hits, to calculate what the pressure is downstream after the shock passes. And we do that here. This is our incoming pressure. We add to that this 18.32 PSI, do the delta, and we get a downstream pressure after the shock passes of 30.65 PSI. We're going to give you a little bonus. This is normally something that's done outside of the lab, and here it is. You guys ready for this? We're looking at the velocity of the shock as measured from the oscilloscope data. We know that the pressure transducers are spaced 30 inches apart, and we know that the time it took for the shock wave to pass from pressure transducer 1 to pressure transducer 2 is 1.46 milliseconds. So we can calculate a shock speed here, knowing that 30 inches is equal to 2.5 feet. We convert that into seconds, and we get a speed of 1712 feet per second. That's the speed of the shock as it passed through the two pressure transducers. Sonic velocity in the lab, you guys remember from basic compressible flow theory, is the square root of gamma g RT. And if you run through this, I'm in English units, this is what I use. And so we come up with a sonic velocity of 1128.5 feet per second. We calculate Mach number by taking the ratio of the velocity to the sonic velocity, velocity to sonic velocity over here, 1712 divided by 1128.5, we get a Mach number of 1.5. Okay, we're going to talk about rise time now. Rise time of the pressure transducer is the issue that we're trying to look at here. And you think of rise time of a transducer like this in terms of shutter speed for a camera. You know that if you have a very fast camera, the shutter speed is very, very small in terms of time, and so you can resolve and pick up things that are happening very quickly. In a pressure transducer, the same thing applies. There's a specification value called rise time in the spec sheet for the pressure transducer that tells you how fast the pressure transducer will respond to a step change input. And in this case, the rise time, or shutter speed, think of it that way, the specified value is 1 times 10 to the minus 6 seconds. That is, 1 microsecond is how long it takes that pressure transducer to respond to a step change in input. So if I graph this out, this spec value of 1 times 10 to the minus 6 seconds is the time it takes for the pressure transducer to respond to a step input like we're seeing with the shock wave. So that's what that is. And what we want to do is compare that rise time with the event time. Now the event time from the standpoint of the pressure transducer is the time it takes the shock wave to pass over the face of the pressure transducer. So think of the pressure transducer as looking at the world through a little opening that's about 0.218 inches in diameter, and that's what I've drawn here. So here's the diameter of the pressure tap poking through the hole in the side wall of the shock tube, and we've got the shock wave coming by at 1,712 feet per second, and it passes over the face of the pressure transducer in a certain period of time. That time is equal to the distance divided by the velocity, and the distance here is the diameter of the pressure transducer. We're going to divide that by the velocity of the shock, and we're going to convert that, of course, into inches per second, and we get a time of 0.0000106 seconds, or 1 times 10 to the minus 5th seconds. This is how long it takes for the shock wave to pass over the face of the pressure transducer. Now the nice thing that we see here is that this event is relatively slow compared to the rise time, the capability of the pressure transducer. And that being the case, then we can say that this event is so much longer than the rise time of this pressure transducer that we are accurately able to capture that event. If it were the other way around, if our rise time, the spec value of the pressure transducer was 1 times 10 to the minus 5th, and this event was 1 times 10 to the minus 6 seconds, we would not have enough response speed to actually pick this up. So think of this rise time as a temporal resolution capability of the instrument.